The introduction, and also it's a really great workshop to be here, and so thank you, Fernando, for the invitation. It's really a pleasure. So after the talk of Lu Wang, someone can just use half of her introduction. So and not only I'll remind you a bit, and not only can I use her introduction, but also what I will be talking about today is heavily using results of Lu and Jacob, so it's sort of doubly depending on their work. Okay, and in the beginning, actually, when we worked on this, we thought it would be a 5-page note, and actually in the end turned out that the estimates we need are quite a bit harder, so that's why I want to talk about it. Okay, so this is joint work with Alex Deruel. Okay, so what do we consider? And I'll try now not to copy all of Lu's introduction. I'll give a bit more introduction on why understanding expanding solutions is actually interesting, and why this should give, in the long run, better understanding of mean curvature flows through singularities. So let's consider a smooth, closed, embedded hypersurface, and let's assume that B its maximal more smooth evolution via mean curvature flow. You always know this exists. And now, if this is not a very sort of simple example, we will have singularities before the surface can vanish, and sort of as possible evolutions, of evolution past the singularity, we can sort of consider here the level set flow. And so level set flow is you can define it as the maximal set theoretic subsolution. So it's more or less level set flow. It's more or less the solution which, if you have non-uniqueness after singularity, which contains all possible evolutions. So it's, in that sense, sort of understanding the level set flow means you understand all possible sort of non-uniquenesses you could get after singularity. So what is the non-uniqueness? This is sort of corresponds to fattening. And let me just draw this picture again from Lu yesterday. We had seen sort of if we have sort of this double cone, for example, then let's assume just that we would have an initial surface. We just take the cone as an initial condition. Then we saw that there are actually different solutions coming out of this cone. We had this two-sheeted evolution here, but we also had this catenoid-shaped evolution here, and then maybe there's even a second evolution inside here. So you see there's different ways of evolving this here, and I'll explain this more later. There's actually there's a way to kind of form singularities which are sort of modeled on these cones, and then you expect actually when the solution passes the singularity, then actually there are different evolutions. You see here the level set flow would be now something which sort of contains all these possible evolutions here. So would be this here. And this is why this is called fattening, because suddenly sort of this set sort of which containing these solutions is not anymore n-dimensional. So what is the question I want to sort of talk about today? Question is sort of uniqueness, non-uniqueness past singularities. This is just more or less the guiding principle why this is interesting, and let's just remark why is this also interesting for weak flows. Because most of you will be aware of the recent work, for example, of Bamler and Kleiner for Ricci flow, proving sort of the generalized Smale conjecture. And one of the central points of this proof is that actually they study sort of really the weak Ricci flow in 3 dimensions, really going into the singularities, going out, and then proving that this solution is actually unique. And out of there they get that this is actually depending continuously on the initial data in the right sense, and that was one of the main tools for attacking that problem. So in the same sense, I think one can expect that understanding non-uniqueness in mean curvature flow will also allow sort of to use mean curvature flow to attack other problems. Now, what do we consider? So consider x0t, a singular point of the flow. So just you can easily define it that there's no backwards parabolic neighborhood of that point where the surface is smooth or has bounded curvature. So this is a singularity forming. What do we know from the monotonicity formula? And we know that at a tangent flow, so it might be several, call this m prime t. T is now only less or equal to 0. At x0t is self-similarly shrinking. Okay, so this is singularity model, at least one of them. Now let's for the moment restrict to dimension 2. So 2-dimensional surfaces in R3, because there the most is known. So what is known there? So Ilmanen proved in his notes, I think this is 95, that actually the tangent flow is smooth. So it's a smooth shrinker. So it's not a shrinker, does not have singularities, but what is not resolved is sort of up to multiplicity. But this is a truly 2-dimensional result. Uses Gauss-Bonnet heavily. But at least you know this much. So you see a smooth shrinker there, maybe with multiplicity. And then here's sort of this famous multiplicity 1 conjecture. Also due to Ilmanen. States that actually no multiplicity occurs. So if you start with something embedded, then if you look at the tangent flows, let's just do the first singular time. Let's talk about past singular, sort of after the first singularity. But then the hope is that no multiplicity should be occurring there. Now, so there's hope that this is true. Now, Lu has also proven a really beautiful results in, I think, in 16, showing sort of she studied sort of the space of all possible shrinkers, smooth shrinkers in R3. There's the following result: any smooth finite genus shrinker in R3, so 2-dimensional, has only cylindrical and conical ends, and smoothly conical ends. Okay, so first one should note that just from being a shrinker, you can always very easily see that you have in a weak sense always only conical ends. This just comes from self-similarity. What she was able to prove that actually these ends are fully regular. So you either see an end with a cylinder, or you see a smooth cone which opens up.
Can you have an infinite number of ends?
I think no. If you assuming probably by the bounded entropy, then no.
Yeah. I would expect that bounded entropy sort of.
Is that known, or that's the?
It's not proved by me, but I think it's true.
Okay. Good. Now, but so Now, Lou has also shown in previous work that if you have an asymptotically conical end and you have two shrinkers which have the same asymptotically conical end, then they have to coincide. So already one end completely prescribes the shrinker, but you need a smoothly conical. The case where you have a cylindrical end is still open in general. Yeah? So this is the cylinder uniqueness conjecture. This is also due to Ilmanen, which just states that if you have a cylindrical end, then you already get that it's the cylinder. And I think Lou has proven that if you have faster than polynomial decay to the cylinder, then you actually get this uniqueness, but establishing this faster than polynomial decay is difficult. Yeah? But I think you also have counterexamples that if you only have polynomial decay, then actually there are not embedded solutions, but at least there are solutions. So this is you might need something like this. Okay, so let's assume that all these conjectures are true. So this means we would expect that we see only cylinders or smoothly conical shrinkers. So this is what this would imply. Let's now distinguish the two cases. So the case one would be we see a cylinder. There's a shrinking cylinder. Okay. And then also there's already some very recent result of Choi, Hasselhofer, and Hershkovitz a few weeks ago. So they also established a conjecture of Ilman, and they established the mean convex neighborhood conjecture. So which states, so you see this, if you see a shrinking cylinder, the cylinder is mean convex, but that's only an infinitesimal information. And the question is, does this pertain to a macroscopic level? So what they then get is that actually there's really around the singular point, there's a little backwards parabolic cylinder, even forwards I think, that the solution actually is mean convex. And that allows them, then you can use a bit older result of Hershkovitz and White. So Hershkovitz and White, I think from, let's see, from when is this? From 17, which then says that if you have only this singularity, then the level set flow does not fatten. So this means these kind of cylinder singularities, although there can be many and they're hard to control, but they don't disturb uniqueness. This is analogy to Ricci flow in 3 dimensions. What is also just important to know by work of Kolding and Minicozzi, we know that if we see one tangent flow as a cylinder, then any tangent flow is a cylinder, and the axis actually is unique. But I don't think that it's actually needed in these results here. Okay, let's do case 2.
Felix, I think they do use. I think that this 18 result uses that.
They use it? Yeah. So I haven't read the proof, so. Now let's assume that the tangent flow is asymptotically conical, or 1. Yeah. Now let's assume one further assumption. Yeah. Assume it's the unique one. Is the unique tangent flow. So it's the corresponding result to Kolding Minicozzi in this asymptotically conical setting. So you don't see different tangent flows at different scales. And what you then get, that actually then means that you can actually go to the singular time m capital T, yeah? Then m capital T is smooth around x0 with an isolated conical singularity modeled on the asymptotic cone of this tangent flow. Okay, so then you can actually go to the singular time, your flow stays smooth, and it only develops one singular point. And that singular point is modeled on this cone. So you really get this picture here that your surface sort of at the singular time looks like this, for example, like this double cone here, but then starts sort of, if you go out, might deviate from the cone. But you get this here. Okay, so in this sense, sort of, now, if you want to try to understand sort of how to flow out of this, is sort of a natural thing to try to understand flowing out of surfaces which are smooth, but which have isolated conical singularities. So what is the first thing? Non-uniqueness, or uniqueness, or non-uniqueness. So what do you want to understand? Sort of understand possible evolutions of this, let's say, tangent cone of the, call C, yeah?
The conical and the anything.
Yes, there's no curve. There's no. It has to be the cone which comes from the shrinker, but I think so far there's no big understanding. There's no equation you can get on the cone. Okay. Now, so if we understand possible evolutions of C, then we hope that we can say something about non-uniqueness or uniqueness, and how the flow should look like, sort of a short time after flowing out of that singularity. What you, for example, can show, if this cone evolves uniquely, then any solution like that also evolves uniquely out of there. But it could happen that actually the cone evolves non-uniquely, but this evolution is still unique. It might be possible that the cone itself has different solutions coming out of there, but the solution itself somehow still pulls in a certain direction and makes sure you only take one of them. So it's not clear. So the point is that if you take the level set flow of this here, of this initial condition here, you rescale it, then it only needs to be contained in the level set flow of the cone. It's not equal to the level set flow of the cone. So it's only an inclusion. Okay, but at least sort of understanding this will help. Now, we have seen from Lou, now I sort of can really copy at sort of a natural evolution are self-expanders in Rn+1. So one thing, if C has a unique evolution, just by uniqueness it has to be self-similarly expanding. But it's also important, even if it's fattening, so fattening would be kind of, you see here. So let's see at time 1, your solution maybe, you see this one, you see this guy and this guy. You can always prove that these boundaries here are expanding solutions. So even in the non-unique setting, understanding sort of these boundaries as expanding solutions is important. So yet in Rn+1, sigma asymptotic to C, and the equation is that the mean curvature vector of sigma minus x perp over 2 is equal to 0, and this is equivalent to saying that square of t times sigma is the mean curvature flow. So at t equals 0, that solution goes in Hausdorff distance back to the cone, converges smoothly always everywhere away from the origin. At the origin the convergence is worse. And okay, now, but we've seen that there's actually also a variational principle for expanders, which is very helpful. So also have that sigma is an expander if and only if sigma is a critical point of the following functional. And we just sort of try to find a good name for it. We call it the forward entropy. Don't know if the name is so good. But at least in this case, it's really hard to move the base point. E of sigma e to the minus x squared over 4. You see here, here's the, say for a shrinker, we would have minus x squared over 4, but this is plus x squared over 4. Now you see the problem is here, we start with something which is a cone, and something's asymptotically conical. So that number actually, if you really want to compute, is always infinity. Because you have this exponentially growing weight at infinity. But you can still ask that this is a critical point with respect to compact variations. That's still well defined. But in sort of a today talk, it would actually be important that this is sort of a very badly behaved functional. But nice thing is, having here the positive sign makes this a convex functional. So it's again sort of the area functional in a conformally deformed metric. So since this is a convex functional, you can just do straight minimization, and this is this existence theorem, which already Lou stated, which goes back to an idea of Ilmanen. And this, I think, is in 95. And you can find sort of the details were worked out by Ding in 13. And it states that let's only do the smooth case, n between 2 and 6, given a regular cone, C in Rn plus 1, then there exists sort of a minimizing. Sort of minimizing always means with respect to compact perturbations, minimizing self-expander sigma asymptotic to C. We've seen the pictures. Also, this dimension restriction is only for smoothness. In higher dimensions, you then get small singular sets. But also important that if you're far enough out on the cone, these expanders are always smooth. So the singular set is always sort of somewhere in some fixed ball of a fixed size. Okay, now, okay, but at least there's a minimizing guy, and that if you think a bit of physics, in some sense, would be the question, at least, if like the minimizing guy is some kind of preferred evolution. But if you want to put in a minimizing guy, then the first question is, it's at least maybe the minimizing guy unique. Yeah? So this is the question I want to address today. Uniqueness of the minimizing expander. And you see immediately that uniqueness in general cannot hold. Here's the simplest example. Just take two lines in R2. You have two possible evolutions, one going this way, one going these ways. If you have a right angle here, there's symmetry, clearly non-uniqueness. But you could ask now, sort of, can I wiggle the cone a little bit and get uniqueness? And that's what I'd like to talk about today. Okay, now, since we have, this is again, so these expanders are minimal surfaces in the right metric. So we can sort of try to sort of think a bit what is known for minimal surfaces. So there's this famous theorem of Brian White. I think it's out of his, actually going back to his thesis from 87. And this is based on ideas of John Morgan. So I looked it up this morning. Let n be a compact m-1 dimensional. And he wants analytic. Not completely clear to me why he needs it, but I think you can always make an analytic. Manifold. Then let B be the set of embeddings. So these are the boundary values. in ck alpha, which that bound two or more stationary, so it needs only stationary surfaces with the same area. Then the statement is then B is meager. So it's of first bare category. Yeah? So you can find, if you wiggle the boundary values a little bit, then, and you fix the area of the surface, then there's only one. Which gives you, for example, immediately generic uniqueness of minimizers. Okay, so what is the proof idea? There are two main ingredients. The first idea is that the projection, the natural projection pi to the boundary values, is Fredholm with index 0. So this first means you can throw away already, then you can do Sartre theorem and throw away all these boundary values which bound degenerate minimal surfaces. So you can assume that all the minimal surfaces they bound are non-degenerate, so have no vanishing, no Jacobi fields, and there are no non-vanishing Jacobi fields that you can throw away. And then the other idea is you look at this functional with the same area, and you try to move, you try to compute the derivative of this functional. And you see you get a term on the functional. If that boundary term vanishes, you can use unique continuation and conclude that then then the two minimal surfaces have to coincide. And that means that actually this map is a submersion. And that means the pre-images has codimension 1, and that immediately gives us. So that the other important ingredient is this unique continuation. At the boundary. Okay, now what is known in the case of expanders? That's where sort of Jacob and Lou have already done a lot of the hard and I guess not always so easy work. So Jacob proved in 1917 unique continuation at infinity for expanders. So what does this mean? Assume you have two expanders going to the same cone at infinity, and their decay rate towards each other is below a certain threshold. Then they have to coincide. So the decay rate at infinity gives uniqueness. And the second paper work is of Jacob and Lou from this year, or also from last year, which says that the space of asymptotically conical expanders is a Banach manifold. And the natural projection, more or less to the link of the cone, pi is Fredholm of index 0. Okay, and if you see this, these are the two main ingredients actually that Brian needed to make his argument work. So we saw this and said, okay, maybe we can get a uniqueness statement out of this. So what is the problem? Is the non-finiteness of the entropy or energy. If this would be a finite number, we could start working. It would be a nice smooth function. Okay, now let's try to make this into a finite number. So let C be a smooth cone, smooth regular cone. So only singularity at the origin. And let's say sigma 0 and sigma 1 are expanders, say smooth expanders asymptotic to C. Then we look at the following quantity, E sigma 0, sigma 1 up to radius r. We just we integrate e to the x squared over 4, intersect this with sigma 1, and we take the difference to sigma 0. Okay. And see this for every finite r, this is a finite quantity. So we hope now to prove that as we let r go to infinity, this goes to a nice functional. But we'll see it's not so easy because this is a really badly exploding weight. Yeah? So to get anything like this, these two guys here have to be very close to each other. They more or less have e to the minus r squared over the 4 decay, at least, to be actually in the realm where we can sort of talk about something. So this is also, when you first think of this, you think, oh, maybe we can renormalize against the cone. Yeah? But that does not work because you can very easily see that in general, if the cone is not minimal, then you have only polynomial decay towards the cone. So against the cone is not possible. If the cone is minimal, this works. Because in some sense, a minimal cone is in a weak sense an expander again. Yeah? Okay, now this is the first theorem. It says the following. If you take the relative entropy, E of sigma 0, sigma 1, you take the limit as r goes to infinity. This is well defined. But even more. So let CS be a smooth family of cones. Say S in say minus epsilon plus epsilon. So what does this mean? This means we move the link of the cone smoothly in S1, in Sn, in the unit sphere. And let's assume we have a family of expanders asymptotic to this family of cones, sigma 0 S and sigma 1 S be asymptotic, be smooth families. And smoothness is now in the sense of the work of Jacob and Liu, yeah? Of expanders asymptotic to CS. Okay, so we have cones here. Very simple picture. Take a cone, you move the cone. Now you think always that you have like two expanders each time asymptotic to this cone, and you move these in a family, yeah? And then the statement is then E of sigma 0 S, sigma 1 S is C1 in S. It's actually a C1 function. And you can even compute the derivative. I won't write it down, but you can write down the formula for the derivative. Yeah? The formula of the derivative comes in form of a scalar product, maybe for the experts. Yeah? You take the variation vector field along the cone. Yeah? This gives you a variation vector field along the link. And there's something, if you have these two expanders, you more or less need to know the decay rate. Then you can define a trace at infinity. You more or less take the difference and rescale the difference in the right way as you go out to infinity. That gives you a quantity which is called a trace at infinity, and then the derivative is a right scale, sort of a right multiple of the scalar product between the normal speed of your variation and this trace. And the important thing is about this trace to know is Jacob exactly proved that if the trace vanishes, then the two expanders are unique. So this means this family has non-vanishing derivative if and only if they're equal. So this is the same setup as before. This is this unique continuation at infinity. Or no, it depends always on the direction, but so what you get from there, this is the next theorem. As expanders, now you can do the with vanishing relative entropy. Let's call this the relative entropy here, this limit, are generically unique. That's a bit of work and sort of look at okay. So then, what is the corollary from this? Sort of that actually the minimizing expanders are generically unique. This means if we wiggle the cone a little bit, there's a unique minimizer. Yeah? Okay, and we first did this formal computation. I thought, okay, this is doable, and in the end it turned out the estimates are much harder than we thought.
Just one question.
Yeah.
To be sure that I understand the statement, you mean that if you have sigma 2, sigma naught and sigma 1 such that E of sigma naught and sigma 1 is equal to 0, then sigma naught
No,
is
if
equal to 1?
yeah, if it's equal to 0.
This is the unique.
Yes, yeah.
And minimizing means that sigma bar sigma 1 is positive for.
No, minimizing only means in the way how Ilmanen constructed the minimizer. So this is, I should say, this good question. You can check. So this gives you an ordering between minimizers here. Yeah? This relative entropy, and you can check that being minimizing, you're also a minimizer of the relative entropy. Yeah? So this is a brief estimate where you have to sort of look at two expanders asymptotic to the same cone. You cut out at a radius r, and you get an estimate on this difference here. If you know how, if you can control this height in a good enough way, then in this limit you can look at this limit as r goes to infinity. You can use that they're minimizing before, but the error which you make by adding this little ribbon here is so small, that you get the inequality in the limit. So this uses sort of a decay estimate, uses the decay estimate of one expander towards the other, and then you add this little ribbon. So see, now you have a compact perturbation. So now this is just a compact perturbation of this one. If this error is very small here, and this is a minimizer, and if you can show that the error as you go out to infinity goes to 0, then you know it's also minimizing the relative entropy. So this gives you then this statement.
So, Felix, sorry.
Yeah.
Why does the corollary follow from theorem 2? I didn't get that part.
Okay. So the idea is, you assume you have an expander which is minimizing. Then a simple picture here. Two expanders going out here. And you look at the height at radius r between them, and you can estimate that this height, this is less than r to the minus n minus 1 e to the minus times the constant r squared over 4. Okay? Now, you know this guy is minimizing. Now, as a competitor surface, you take this ribbon here plus this part. Now you compute the contribution you get from this ribbon in this functional here. Yeah? And that decay is good enough to make sure that this contribution you get from this extra ribbon goes to 0 as you let R go to infinity. So this means that a minimizing guy has minimal relative entropy with respect to any other expander. Okay, but assume you have two minimizing guys, then the relative entropy between both of them has to be 0. You just play the game. Yeah, thank you. Then they both have relative entropy 0, and then you have uniqueness. More or less in that sense, you can really look at this relative entropy as an area. Then you know that the relative entropy of sigma 0, sigma 1 is less or equal than 0, and if the other one is also, you swap the roles, it's also less or equal than 0, and then you're done. But it crucially depends on this estimate here. If this estimate wouldn't be good enough, you wouldn't get anything. Okay. So. Okay, now give some proof ideas of theorem 1.
So, Felix,
Yeah.
So you said that minimizing expanders,
Yeah.
their relative entropy is 0.
If you have two minimizing ones, their relative entropy is 0.
Okay. And thus they are.
They have vanishing relative entropy.
Because then the ones with vanishing relative entropy generically are unique.
Yes.
So this example you started with, where non-uniqueness does not hold,
Yeah.
where you have these two different guys, so they're vanishing.
They are also,
Entropy is 0.
yes. But that's one of these examples where you don't get uniqueness. But it's clear, if you have a symmetry in your problem, that already forces it. Okay. What you start to do this, so what you need to make sense of this, we need to get estimates of how close one expander is to the other. Now, what you can do, you can write sigma 1 as a normal graph over sigma 0 with height function u out on the end. Let's say u is from sigma 0 without a big ball of radius r to r. So it's just writing so that the ends, you can prove they're all nice smooth graphs over each other if you go far enough out. And then you can check what there's a PDE that there. So then you sort of write the Schrinker equation of sigma 1 as an equation over sigma 0. Then you satisfy the following equation. More or less, you get the linearization. So what is the linearization? This is this drift Laplacian here. Plus minus u over 2. This comes from the x comma nu, and then you get junk, sort of higher order junk. And what you first can prove is that the first estimate is that q of x u nabla u. This is, you can bound this by a constant times r to the minus 2 times modulus of u plus r to the minus 3 times grad u. These are the important terms. Okay, and then that is actually enough to use a maximum principle, a non-compact maximum principle, to prove the following, that u is O of r to the minus n minus 1 e to the minus r squared over 4. You know that the difference goes to 0 at infinity. That's the ingredient you use.
Why does the difference go to 0?
Because they're asymptotic to the same cone.
But if you have one guy and you move it,
we're working only over the same cone. At the moment we're not moving the guys. This is the much more difficult thing later. So at the moment we're only looking at the case where we have two expanders asymptotic to the same cone.
So what does it mean to be asymptotic to the cone? I mean,
you can prove it's
right at which you
the height function goes like 1 over r, and the gradient goes like 1 over r squared. So it's really nice, smooth graph at infinity.
So if you have a guy which is asymptotic to a cone, if you move it perpendicular, say distance 1, this second guy is no longer asymptotic to the cone.
No.
Even if it looks
No,
like it's
no,
still-
no, no, no. It's not the same cone. So it really has the same. Already this height function, you get very quickly a priori estimates that this height function has to go like 1 over r, and gradient has to go like 1 over r squared. So this you get very quickly for free. Okay, you can then you can improve this. If you have this decay, you can do
So
a Yeah.
so then that guy is asymptotic to a.
Pardon?
If you have a guy which is asymptotic to a cone, and then move it in the normal
We're
direction.
not moving anything at the moment.
So if you just
We only have one cone and 2 expanders asymptotic to the same cone. And we're only looking at the difference between 2 possible expanders. The moving later will be more difficult. There it's exactly, there's a problem because you only get a linear growing part. But that's exactly right. That's the next thing you need. If you want to move things, that's what you have to consider.
Felix,
Yeah.
in that estimate for Q
Yeah.
symbol there,
Yeah.
it's,
Less or equal.
yeah.
No, so there's a maximum principle, and you can even prove, so then the corresponding gradient estimate is not on the gradient of u. That doesn't behave nicely, but actually you have to rescale u first. You can prove that gradient of r to the n plus 1 e to the r squared over 4u. So you take the first scaling out. That is O of r decays 1 order faster. And this is also, you can do just by the maximum principle, but just important also alternatively, you can, Jacob has proven integral estimates. Which is completely correspondent to these soup bounds. But then you don't get, but the point is in the end for another argument we needed to add here an error term and then to go through Jacob's whole machinery was a bit too much work, and then we realized that actually we can do it with a maximum principle in 2 pages or 3 pages, and we said okay, let's do it with a maximum principle. Because he really needs the frequency function at infinity, and it's pretty hard. Okay, now how do we do the localization? And it's interesting that even with these estimates here, you think like, oh no, I'm done, I've won. Yeah? You think, okay, this is good enough. If I look at this difference here, finite radius, that should me tell you that this is a Cauchy sequence in R. But actually, if you do the computation, just put this estimate here in, it's not enough. You still get an error term which is growing. So this is just putting in this first ED soup estimate, I think, oh, I've won, I can put this in here, I've done. You're not done. There's another geometric observation you need to use. So do the following here. You take let's do this a bit more precise. Take a cutoff function phi. Just as follows, you take it constant to -1 for negative, and then you cut it down smoothly and say this is delta here. Okay? This is your phi. Then you consider phi r. It's just phi of r minus capital R. So you take it radially symmetric, and you just make sure this cutoff happens at radius r. And then you look at the following quantity here. Since this is easier to differentiate, sigma 1 phi r minus sigma 0 okay, and so this is what we want to estimate. So this is just an approximation to this step function in here. Here. So what we want to use now is that both these surfaces actually satisfy an equation. They're both critical points of the functional. So this is an additional information. So what you do then, you do interpolate between these 2 surfaces. You take sigma prime t is just graph over sigma 0 of t times u. So you just graphically interpolate between them both. So this is the variation vector field. Y is d by ds of sigma prime t. And I say t is in 0, 1. Okay. Now you can just everyone can quickly do the computation here. If you take d dt of sigma prime t phi r e to the x squared over 4, you get here as the first term, this is just a normal term without disregarding the cutoff function, x perp over 2 minus mean curvature times the variation vector field times e to the x squared over 4. Now you get the additional term which you get from the cutoff, e to the. Okay. Now what you notice here, if t is equal to 0, then this term vanishes because you had an expander. Okay, so that term is vanishing at for t equal to 0. And if you look at this term, that term is okay at t equal to 0. That term is, we can show that this term here is O of delta inverse r to the minus 2 times sup norm of u. There's sort of this angle. You have an angle information in here which gives you the r to the minus 2. And that's enough to make this error term to decay. Now the idea is, okay, we want to kind of do a Taylor expansion of this guy here around t equal to 0. Now we compute the second derivative. And now this I won't do anymore, but this is just a normal second variation. You get all these terms, but this is then quadratic in the error. This is quadratic. This is then enough to beat the growing weight. So you use really that you start off from a critical point, and then in t you see this functional this in t here for t equal to 0. If you put in not sigma 0 but sigma t in here, that has derivative 0 at 0, and then you just do mean value theorem, and you compute the second derivative, and then the estimate is okay. So you have to really put in a bit of geometric information here to get the estimate. And if you so this is okay. So the error here is okay of this guy, and if you put this together plus use Taylor, you get then that this relative entropy sigma 1, sigma 2, phi r, this decays like c to the r to the minus 3. And the important thing is the c is independent of delta. So you can prove this estimate here. This means we can start letting this cutoff function go back to the delta function, and we still get the same decay. Okay, and now as André has asked, so this is now the much harder point, which we then actually only while doing this realized. It's the following estimate. Now you want to prove that this thing is C1. So what you do here, you try to vary this guy here while you vary the cone. You go to do this phi r here, this, the one with the phi in there. I erased it already. Oh, no, it's there. If you take this one here, this is nice and smooth. Now you think you'd put in an s here. Now you vary this in s. You see again, both of these are always minimal, so this first term will start dropping out. That term you get will always start dropping out for both terms. You get the error terms, and so what in the end will pop up will be the Jacobi fields for the variation. But the thing is, if you move the cone, the Jacobi fields are linearly growing at infinity. They're not anymore decaying. So there's the one important lemma, sort of this is the last thing I want to say. The main ingredient, and this took quite a while to prove this, to show that this here is, so S here is C1 in S. It's the following lemma. Let Vi I is equal to 0 and 1 be the two Jacobi fields associated to the variation of sigma is, induced by the variation of the asymptotic cone. Cone CS, then, so i.e. what do we have? We have two Jacobi fields, Laplace sigma I vi plus 1/2 x nabla sigma I vi plus norm of a squared minus 1/2 times vi is equal to 0. So this is the Jacobi equation for expanders. Then you can prove that v1 minus v0 still has the same order of decay as the height function. It's o to the r to the minus n minus 1 e to the minus r squared over 4. You see, that's pretty tricky, because a priori both these vector fields have linear growth. So you have to more or less really single out the linear growth and say the difference is already this much better. And in the end, we do it by the maximum principle, by getting error. We compute the difference, get a Jacobi equation for the difference plus an error term, and you have to prove the error term is already very, very fast decaying. And that's pretty tricky, actually. So they actually have to. You can't just brutally estimate, but in the end, you need to use several geometric cancellations. And really look at it, and several terms have to cancel, otherwise you don't get down to that decay. But this is sort of the most important estimate in the end to make when you vary the cone to prove that this is C1 in varying the cone. Thank you very much.
Is there any question? Some more questions?
Is there any kind of uniqueness statement by assuming that the cone is not too bent or something?
I mean, to bend?
Like if the link of the cone is small curvature.
So definitely, if your cone is, for example, graphical, if you can write it as a graph, then there's only one unique expander. I think if the cone is mean convex, then you get only one. You only have a motion in one direction. You get one expander. Do you know anything else, Lou?
In general, I think so. But that's the only case I know. Like a mean convex, they get that in that.
Other questions? No. So let's thank Felix again.